This video covers our investigations on electric motors by Group 4B. During this lab, we explored if the speed of a homopolar motor could be changed by changing the current. It was hypothesized that increasing the current through the circuit would increase rotations of a wire loop, which represented our motor. Because of interactions between the electric and magnetic fields, increasing the current was achieved by increasing the number of batteries, which resulted in an increase in motor speed. Our results indicated that current and motor speed are directly proportional. The right-hand rule is key to visualizing the perpendicular relationship between the vectors of magnetic field, current, and force. Throughout the experiment, magnetic field stayed constant because the number of magnets was consistent. By changing the number of batteries, we were changing the current, which was our dependent variable, and the resulting motor speed was the independent variable. We assumed that the batteries were not losing voltage over time because the batteries were only being used for a short period of time and should have provided a constant supply of voltage. Next, the individual magnets we used were the same size and shape, so we're assuming they are of equal strength. Finally, air resistance is negligible because it's not sufficient enough on the spinning wire to affect our results. Magnetic field, force, current, and torque are all directly proportional as seen by the given equations. So, increasing the number of batteries will increase the current, which will increase the magnetic field, which will increase the force acting on the wire loop, which will finally increase the torque and result in more rotations per minute. When a current-carrying conductor is placed in a magnetic field, a torque will be developed on it, hence it moves.
Here we have our magnetic models. The first two models display the force and the current the coil experiences on both halves. The bottom three graphs represent our energy bar charts, which is the type of energy our coil possesses when it is in motion. The last diagram in the far right corner is our system schema. Here's an explanation to each model on the previous page. As already stated, the current and magnetic field must be perpendicular to one another in order to generate a force that allows the coil to spin and act like a motor. This is known as the right-hand rule. With that being said, our energy bar charts represent the energy created while the motor is in motion. Increasing the batteries increased the current, which ultimately increased the force. Therefore, our energy turned from potential to kinetic as the motor was in motion. Our last model represents the current and force in both halves of our loop. The top half of the loop possesses a current to the right and a force away from the screen, allowing it to spin towards us. When we flip the loop so that the bottom half is now on the top, we see the exact opposite direction of current and force. The current is pointing to the left and the force is pointing away from us. Here's our experimental design. We set up our experiment based off the model displayed. We then stripped the wire on one side at both ends using sandpaper. Then we attached alligator clips from the battery to the wire holder so that the current could flow through. Once that was done, we began to measure the voltage at the battery and the current at the wire. This was done 4 times as we added a battery for each trial. Then we began to measure the speed of the coil using iMovie. Each trial was recorded for 10 to 20 seconds as the movie analyzed the videos from frame by frame. This gave a time frame of approximately 10 seconds, and the observed revolutions per second were then converted to revolutions per minute. Here's our raw data displayed in the table. Voltage was measured at the battery during each trial as we continued adding batteries in each trial. The current was also measured at the wire during each trial. Lastly, our speed was calculated through the trials using iMovie.
Here is the graph for current and voltage where we can see a direct positive linear relationship. Here we have our motor speed plotted against our current. We can see a strong positive linear correlation between the two variables. Now for the physics interpretation. The stripped underside of the wire allows current to flow through the loop. Since the loop is under a magnetic field, the current feels a force. These forces work to turn the coil. It's important to note that for this force to be felt by the current has to be perpendicular to the magnetic field. This is observed through the right-hand rule. Furthermore, only one side of the wire must be stripped so that the loop can make one complete turn. If the wire is not stripped, oscillation of the coil would not be seen because no current would be flowing through it. The number of batteries increases the current due to Ohm's law. Batteries supply a constant voltage. Therefore, if you increase the number of batteries, you increase the voltage, which is directly proportional to the current. As we increase the current flow, there is more interaction between the electric and magnetic fields. This increase in the force magnitude will increase the speed of the motor. This is depicted on the graph above as current and speed are directly related to one another. Since only half of the insulation was removed as the electromagnetic rotates, it turns off, gliding through the second half of its turn, only to repeat the process. We've learned that increasing the current by increasing the number of batteries will increase the speed of the motor. The loop spins faster when you increase the current due to the force of the cross product. As one increases the current, the magnetic field will increase due to moving charges. Ultimately, the force on the coil will increase, which allows the loop to spin faster. Our model represents an accurate representation of a motor found in a toy due to the similar setup of our own experiment with a motor involving a permanent magnet, a battery, and the fact that a small toy DC motor often operates on 1.5 to 6 volts. Both the toy motor and our motor can vary speed based on a changing voltage/current. Reasons for error include that the thin wire supporting the loop could have been a source of error because as the coil spun, it created a slight bend in the supporting wire, which made the coil spin slightly differently than when the wire was straight. In addition, there may have been air resistance playing a role, which we neglected in our calculations. Finally, due to the number of spins being counted by hand, there may be human error in the raw calculation.